All right, so this number 13 is an example that ties together a couple things that we did in limit laws. So we saw problems in limit laws where we're given a graph. In this case, this is f of x, this graph here. But they also give us some values of g of x and h of x. I forgot to put h of x there, but you can see we're given that information here as well, right? That the limit as x approaches 2 of g of x is 5, and the limit as x approaches 2 of h of x is 3. Okay, so then we're given this this big limit expression here, and we want to use limit laws to break it up, right? Because as it is, we can't really evaluate that because that's we don't know exactly what g of x and h of x are, with that combined function, with that collective function. So we do know what they are individually. So if we can break it down into situations where we see this and we see this, and we see what, something we can evaluate on the graph, then we can evaluate those individually and then use the operations around them. So so we're going to do, remember, limit laws. We have our, here I see power law, I see difference law, quotient law, product law, constant multiple, right? So almost everything but maybe like root and sum law, right? And so what I want to do is I want to get down to these individual limits, right? And so basically what limit laws allow us to do is basically we're going to have a limit here with g of x, right? We're going to have a limit here with the constant. We're going to have a limit here, constant multiple, put the constant in front and take the limit of f of x, and then we'll have a limit here, right? And so again, this one uses the power law to be able to say that we can just take the limit of g of x and then square it. The difference law, just by just saying we can the difference of the limit of a difference is equal to the difference of their limits. Constant multiple we talked about, and then the product law says the limit of a product is equal to the product of their limits, right? So when I rewrite this, it's going to look like this. It's going to be limit of g of x quantity squared minus the limit of 4, and all of these are as x approaches 2, right? And then all over 7 times the limit as x approaches 2 of f of x times the limit as x approaches 2 of h of x. All right, so the benefit of this is now we know what this equals, right? Let me color code this. So the limit as x approaches 2 of g of x is this value right here. So I'm going to put in a 5 right there. So this will be 5 squared, right? Minus this one we know, right? Remember the limit of a constant. Let me just write this out. The limit as x approaches a of a constant is just the constant, right? Also remember the limit as x approaches a of x is just a, right? So those are kind of our fundamental laws. So I know this is going to turn into 4. All right. Then on the bottom, we have 7. And then this here, the limit as x approaches 2 of f of x, that's something we want to evaluate on the graph. So as I approach 2 from the left and from the right, my output approaches 1, right? So my output approaches 1. So this will be 1 here. Okay. And then finally, I want to find this here, the limit as x approaches 2 of h of x, and I can see that that's 3. So I'm going to multiply that by right there and put in a 3. All right. So that's basically what that all boils down to. So we used our limit laws to break up our limits, to kind of break it down. And then we're able to get it into a place where we can just use some order of operations work to figure out the answer, right? So it'll be 5 squared is 25 minus 4. So that'll be 21 in the numerator. And then 7 times 1 times 3 is also 21. And so we'll get 1 in this case. All right. So again, something we couldn't have done necessarily collectively as it was, but when we break it down using our limit laws, we're able to get it to a point where it just becomes some inputting or substitution and then evaluation using PEMDAS.